Greetings once again from sunny Northern California. Yesterday I talked about dark matter, its characteristics and its role from the perspective of Vedic cosmology. Today I'm going to provide or propose an alternative to the standard model from the perspective of Vedic cosmology. A working hypothesis of a cyclic universe that neither undergoes cosmic inflation or a contraction or a big crunch. But before I do so, let's recall some of the major points from yesterday's talk. That forms the basis or the background of today's presentation. Recall that Vedic cosmology correctly predicts or describes or indicates the useful lifespan of the sun, the age of the universe and of the Milky Way, Earth's incineration in the next 4 to 5 billion years, preceded by boiling over of the oceans and a greenhouse effect, the existence of a 13.2 billion year old solar system in the Milky Way, the morphology and constituents of a structure resembling a proto-galaxy. And lastly, the three constituents, and the most important one, the three constituents of the universe: ordinary matter, dark matter, and dark energy. Furthermore, VC suggests, indicates, or implies. These are important. These become the basis, if you like, of the model itself. The universe has undergone an unknown number of cycles, each lasting 311 trillion years. The current cycle began roughly about 14 billion years ago, as we know from Standard Cosmology. Only dark matter and dark energy existed at the beginning of the current cycle. That's an important point to note. Only dark matter and dark energy existed at the beginning of the current cycle. Ordinary matter is a product of dark matter, created at the beginning of a cycle and converted back to dark matter by the end of the cycle. Time is without a beginning and its end is not known. Space is apparently unbounded and exists in virtual perpetuity. The density of dark energy is uniform in space and time. That's the same thing as in Standard Cosmology. The density of dark matter, on the contrary, is virtually constant in time but not in space. That's an important distinction between Vedic cosmology and Standard Cosmology. We conclude, therefore, the universe is a self-perpetuating closed system in which nothing is created or destroyed, conserving mass and energy. So let's begin the working hypothesis. What were the initial conditions at the beginning of the current cycle? The universe or space was uniformly filled with dark matter and dark energy, within which existed, and that's the proposition, at least one supermassive gigantic black hole. We will call it the mother black hole, exceeding trillions of solar masses. That's an important point. So the space is totally uniform. The largely uniform background canvas of dark matter was punctuated by, or scarred, if you like, by density in homogeneities, with a network of overdensities marking the sites of black holes, galaxies, and galaxy structures in the previous cycle. The idea is simply that once the background, the dark matter, is scarred with the locations of the galaxies and clusters of galaxies and black holes from the previous cycle. That's an important point. The average temperature of the space of the universe was near absolute zero. There was little or no ordinary matter and radiation left over from the previous cycle. And the cycle begins with a bang, just as in Standard Cosmology, about 14 billion years ago, with an explosive release of ordinary matter and radiation from the mother black hole that expands outwards in all directions, forming an expanding luminous, important, luminous universe, a visible universe. So this slide shows you the schematic representation of the universe and its densities. On the left side, what you have is, right in the center, the black dot represents the mother black hole from which matter, ordinary matter, and radiation emanates. Surrounding it is the luminous, expanding, luminous universe that has both dark matter, dark energy, as well as ordinary matter. And on the outside, the B part, is where there is only dark matter and dark energy and no ordinary matter. So bear in mind these three distinctions. The black hole is only important right in the beginning, explosive release of material from it, thereafter it ceases to exist. On the right side, you have densities as a function of time. At the bottom, number one, that's the density of dark matter. In this model, or working hypothesis, the density of dark matter is virtually constant in time, but not in space. Then number two, that's the density of dark energy, which is the same as in Standard Cosmology. It is constant in time and space. At the top, you see that's the combined density of dark matter, dark energy, and ordinary matter as a function. It asymptotically decreases from a very high number at the beginning to basically the combined density of dark matter and dark energy. So let's look at how the structures form in this case. Dark matter does not travel as the luminous universe expands. So, therefore, dark matter is cold and not warm or hot. Remember that in Standard Cosmology, it's difficult to explain why the dark matter is cold. It's assumed to be, but we don't know why. Here's an explanation. In Vedic Cosmology, or in this model, it does not travel as the luminous universe expands. Therefore, it's cold. Hence, those pre-existing overdensities in dark matter, background, begin to grow well before recombination by accreting dark matter from their vicinity, forming lumps of dark matter on all scales, because you have these pre-existing density in homogeneities in all scales, while radiation prevents baryonic fluctuation from collapsing. This growth, possibly aided by gravitational perturbations resulting from the explosive demise of the black hole, lasts at least 400,000 years until recombination. It may continue thereafter, but at least the first 400,000 years, these density, the growth of fluctuations in the dark matter in homogeneities can grow. After recombination, what happens? Baryonic fluctuations collapse on top of the dark matter fluctuations. The baryonic fluctuations seen in the CMB, therefore, are imprints on top of the much stronger dark matter fluctuations. Now, this is important. What we are proposing is, thereafter, very dense gas clouds collapse directly into the larger lumps of dark matter, forming black holes. And once a black hole is formed, it gravitationally attracts additional gas, forming a galactic disk centered on the black hole and surrounded by dark matter halo. Now, the exact mechanism how black holes may have formed is not known. We don't know how this may happen. But the fact, this is an important fact, and this may provide a mechanism. But the fact that the density of ordinary matter in the early universe was orders of magnitude higher than that at the present suggests that the density of the giant molecular clouds that collapsed to form black holes was also orders of magnitude higher than the present day GMCs, or the molecular clouds that collapse to form stars. If So the idea is simple as this. If today GMCs can collapse to form stars, then the same sort of clouds in the early universe, when the density was probably 1,000 times greater, roughly, could possibly directly collapse and form black holes. That is the idea here. This actually may explain why most of the massive black holes and galaxies formed early in the universe, in the first few billion years, and you see very few of them thereafter. As the mass of the central black hole grows by accreting gases or by merger with other black holes, its gravitational reach increases. And so does the mass of gravity, mass of the galaxy, not gravity, composed of gases and dark matter. So the idea is the two are linked. The mass of the black hole is linked to the mass of the galaxy, or vice versa actually. The mass of the galaxy is linked to the mass of a black hole. As a black hole grows in mass, so does the galaxy. Shortly thereafter, stars form, explode, release heavier elements, and some collapse, forming smaller black holes within galaxies. These are the stellar black holes. Eventually, galaxies merge, forming clusters and large structures. So from this section, we can conclude galaxies began forming soon after the onset of the current cycle, preceded by black holes. Older galaxies likely to be the most massive. Almost all of the galaxies with massive black holes probably formed early while the baryonic density was relatively high. Remember that the density of ordinary matter in both models, Standard Cosmology as well as in the Vedic Cosmology, rapidly decreases as the luminous universe expands. Now it's commonly accepted that the universe started expanding, or the expansion accelerated 5, 6, 7, 8 billion or 9 billion years ago. So the important idea is that when did this occur, from deceleration to acceleration? When did it actually occur? In our model, the luminous universe continues to expand, driven by the initial impulse from the mother black hole. Thereafter, it is modulated by the negative gravitational effects of dark energy, just as, if you like, to some extent, as in Standard Cosmology. Now, we can make several predictions. The Hubble parameter asymptotically reaches a constant and not expected to significantly decrease from here on, because dark matter density is constant, as is the density of dark energy. And ordinary matter at the present time apparently constitutes only about 5% of the total energy density. Hence the Hubble constant has basically, according to this model, has reached a constant. Whereas in the Standard Cosmology, since the densities of dark matter and ordinary matter both decrease with time, the Hubble parameter is expected to continue decreasing well into the future. The transition from deceleration to acceleration in a flat and constant dark energy space apparently begins at a redshift z, t in this case, when the density of dark energy equals or exceeds roughly half the density of matter, meaning both dark matter and ordinary matter. And there is I won't go through the equations, but there's a commonly used linear parameterization for the deceleration parameter. This is commonly used, and you can see it on the screen. And if you look at the literature, currently the best estimate model independent. It's very important that the estimate be independent of any model, whether it's standard cosmology or any other model. The best estimate is from Jesus et al. In 2018, who used about 740 supernovae and Hubble parameter data. They get a ZT, the transition redshift, at 0.973. We can compare the predictions of the two models, the Vedic Cosmology model and the Standard Cosmology model. What we get is, going through the different equations, you can reach the following conclusions. 1. The Vedic Cosmology model predicts that the transition occurred at a much higher redshift, almost 1.5, than the Standard Cosmology, which is roughly about 0.5. So there's a huge difference between the two models as to when this transition occurred. Unfortunately, at the present, it is not possible to discriminate between the two models using this as a discriminant, because as you see here, for example, the best available data falls right in between 0.973 or almost 1 is between half and 1.5, right? But as the next slide shows, and I'll show you in a minute, there is a large uncertainty on the determinations on the upper limit or the upper end of this transition because of the spectrum, the Z spectrum of data used. There is a paucity of data from the higher end of the spectrum. The determination of this transition increases as you increase the spectrum. So clearly there is a bias in favor of a later transition if there are no data from the high redshift. So we need data from the high redshift shifts in order to exactly determine as to when this transition occurred. There is another conclusion we can draw. We can also see that we can determine the densities of ordinary and dark matter from the calculations of Jesus et al. It turns out that if you use that information, you get the density of matter at the present, which is roughly 20% higher than that determined from Planck data using Standard Cosmology. This result, in fact, is in accord with the proposition of the Vedic model, Vedic cosmological model. Why? Because the density of dark matter is constant and is expected to be higher than that inferred from Planck data. So at least that much is in favor of our model as far as the density of matter deduced from the calculations or the observations or the conclusions of Jesus et al. More importantly, since the densities of dark matter and ordinary matter both decrease with time, the deceleration parameter should keep on decreasing asymptotically, reaching a value of -1 in the distant future. That is the Standard Cosmology, because the density of dark matter and ordinary matter both decrease. Therefore, the deceleration parameter should keep on decreasing till it gets to be -1. But in Vedic cosmology, the density of dark matter is constant. So it predicts a totally different outcome. It predicts, in fact, that it cannot decrease below 0.493, or roughly -half, if you like. And the current model independent value is 0.43. The conclusion, therefore, is VC predicts that the current acceleration has almost reached a maximum and should not increase substantially from here on. This is a very important conclusion as far as Vedic cosmology is concerned. Because if indeed the acceleration has reached its maximum, very or close to it, it will have a totally different, the outcome for the fate of the universe is going to be completely different. The VC, as I said, the Standard Cosmology predicts that the acceleration will continue to increase into the distant future. A very important distinction between the two. And what's the ultimate fate? It's rather simple. It can be said in a few lines. What does the model envision? The model envisions that massive black holes will keep on accreting more and more gases, progressively gobbling up entire galaxies. Ordinary matter continues to diminish in the luminous universe, so that eventually little or no ordinary matter is left and the luminous universe ceases to exist. So there's no question of acceleration or anything, or expansion. If the luminous universe ceases to exist, acceleration, expansion has no meaning. Then black holes merge through mutual gravitational attraction, such that after trillions of years, only one or a handful of supermassive black holes are left. And one of these black holes becomes the mother black hole from which ordinary matter emanates and a new cycle begins. So in the end, what do you have? You have a universe which was the same as in the beginning. It's homogeneous, isotropic, little or no ordinary matter, only dark matter and dark energy. That's what's at the end of the universe, and that becomes the beginning of the cycle. Now, if more than one, possibly, black holes were to explode, you will have a multiverse scenario. But it's likely that the oldest mother black hole would be the one to explode, in which case it's most likely that you have a single universe rather than a multi-universe. Now this working hypothesis apparently explains a number of unanswered questions in Standard Cosmology. Why the universe is apparently homogeneous and isotropic, we just talked about it. Why the universe is apparently flat is also understandable. The universe in the Vedic cosmology is almost infinite. It does not contract, it does not expand. The universe as a whole does not. Its density remains constant in time. So the universe is flat. We also give you an explanation, or at least an idea or a suggestion, that galaxies, black holes are the ones to form first and galaxies follows thereafter, and therefore the masses of the galaxy is related to the mass of the black hole. It also explains why dark matter is much more abundant than ordinary matter. Vedic cosmology, Standard Cosmology doesn't have an answer. It doesn't tell you why dark matter is much more abundant. In Vedic cosmology, we understand why it's so. Because dark matter is the mother of ordinary matter. And also the so-called cosmological coincidence problem. Why the density of dark matter and dark energy at the present time happen to be comparable. If indeed dark matter was created in the Big Bang in Standard Cosmology and its density has been decreasing. It just happens to be so. But not in the case of Vedic cosmology, because both are constant in time and therefore comparable. And it gives you, the Vedic cosmology gives you an ultimate fate of the universe. Whereas in standard cosmology, we don't know what's going to happen. There are all sorts of speculations. Heat death, the Great Rip, and so on. So We could and also, as I said yesterday, it apparently resolves the so-called Hubble constant tension, the tension between the values in the Hubble constant calculated at the present from supernovae and that inferred from CMB using the Standard Cosmology. So here you have it. These are the outlines of the working hypothesis. It needs a lot of work. There are a number of questions. For example, can a dark hole become a white hole and thus release the information as the material that it gobbled up? There's also the question, Vedic cosmology tells us that ordinary matter is a product of dark matter. So the question arises, if ordinary matter is gobbled up by black holes, not dark holes, black holes may be dark holes in the sense that that ordinary matter is converted to dark matter under certain conditions of temperature and pressure. We don't know that. So these are some of the outstanding questions. That's the end of the talk. If you have any questions, thank you for listening, first of all. And if you have any questions, please email them to me and then try to answer them to the best extent possible. Thank you again. Take care.